Retrieval augmented generation, or in short RAG, was originally introduced in 2020. But since the emergence of ChatGPT and large language models, it has gained a lot of traction. And for the past 2 years, it has evolved a lot. So in this video, I want to go through 8 state-of-the-art RAG techniques in industry. You'll see their use cases, their challenges, how each one of them works, where should we use them, etc. Besides that, I also have prepared a repository that contains each one of those methods. I implemented each one of those methods here so you can use them. And this is how it looks like. So when you clone the repository, prepare the environment, and execute the chatbot, you will have access to a chatbot just like this. It has all the methods that we want to cover in this video, and you can ask different questions based on the vector database that you prepare for it. So as you can see, this is just a simple query here. It provides me with the answer, and on the right, you can see all the steps that happen behind the scene for that specific RAG method that we chose here from the moment that we sent our query up to the time that we got our response back. So this is going to change based on the method that you choose here, and no worries for now. We are going to go through all those details in our presentation and also in the chatbot. So just a quick note, as you can see, there are 9 different RAG techniques implemented in this chatbot. But for simplicity, I decided to combine these two together and talk about both of them at the same time, because the only difference between our standard or naive RAG versus RAG with memory is the additional memory component that we added to our RAG chatbot. So let's also quickly go through the repository for this project. This is my GitHub profile, and if you have followed the channel, you know that one of the projects that I've been working on is called Advanced QA and RAG series. And if you go inside that project, RAG Evolution 8 SOTA Techniques is the new sub-project that I added in this one. So if you clone this project, you will have access to all these projects and you can start interacting with them. But this is what we are going to talk about in this video. And in the README file, you have all the instructions for how to create a virtual environment, how to activate your environment, how to install the requirements that are required for this project, and how to execute the project. We are going to also prepare a vector database, actually 3 vector databases for this project. I will talk about that when we go through the code together. So with that, let's go through our RAG techniques and let's see how and when we can use each one of these methods for our project. So let's begin by standard RAG. I think this is the most important strategy, although it is also called naive RAG because of its simplicity. But if you understand how standard RAG works, you can easily understand how each one of those newer methods or the more complex methods work as well. So a naive RAG or a standard RAG starts by searching a knowledge base for information related to the user's question. So we ask a question, then we also have a vector database that we created off of our documents or our information that we want to interact with. We perform a vector search on our vector database using the user's question. We retrieve the most relevant documents, then we feed those documents along with the question into a large language model to generate an answer. So you can think of it like asking a librarian for books on your question and then having an expert read those books to answer you. In the next step, we can also add memory to our RAG chatbot. And what happens when we add memory to our system is that our system now can remember past interactions or important facts from previous queries. It can also bring in context from earlier conversations or user data when answering new questions. So in simple terms, the AI doesn't start from scratch each time. It recalls what was already discussed, leading to more coherent and personalized responses. So in summary, for standard RAG with memory, we have our query, then we have a retriever that gets the query, performs the vector search, and retrieves documents. Then we have a generator, which is a large language model. It receives the user's question along with the retrieved documents, and it generates a response for us. It also, like the RAG method also has a memory component inside it that we have to update, and we have to fetch information based on the user's question in each interaction. Okay, let's go through some of the use cases. So the first use case is chatbots and personal assistants that remember user preference or past conversations details, and they can deliver contextual answers based on those information. The second use case is customer support knowledge base, which maintains consistent support across users' chat sessions, and it can, for instance, recall past issues to avoid repeating troubleshooting steps. We are going to see an example scenario right here. And finally, personalized recommendations. So imagine that you have a chatbot that has a feature to offer users some new products or recommend them what to purchase next. Based on the information that it has from each user, for instance, their favorite genres or what they purchased before, it can provide tailored answers and suggestions. So let's go through an example scenario here. So we have a tech support chatbot that is using a standard RAG with memory. The user asks, my printer is showing an error code 123 again. How do I fix it? Memory recall, the system remembers that the same user asked about this error last week and had installed a specific driver. Then it also searches against our vector database in order to find the most relevant documents for that specific query. So it searches printer error 123 driver, and it finds a relevant troubleshooting guide. Then we combine everything together, the user question, the chat history that is relevant to that specific question, and also the documents that we retrieved from our vector search. And we pass everything to a large language model. And this is the response. It looks like error code 123 is fixed by updating the printer driver. Last week, I recommended driver version 2.3. Have you installed that already? If not, please download it from, this is the support link that the user can use. And after installing, restart your printer. This should resolve the issue. So this answer, as you can see, is coming from not only the documents that we retrieved from our vector database, but also the information that the chatbot knows about that specific user. What are the impacts? Memory made the response more personalized and context-aware. And in that scenario, a standard RAG would not have referenced the prior interactions. So what are the challenges for these specific methods? The first challenge is memory drift. So as you can imagine, over time, irrelevant or outdated context may accumulate. That also leads to the next challenge, which is the storage cost. So as you can imagine, as the memory grows, we will also need a bigger storage, and that would lead to a higher cost. So we have to manage that as well. And finally, recall quality. So here I said it depends heavily on embedding accuracy. Poor embedding leads to poor memory. Keep that in mind. Memory is probably the most difficult component inside a chatbot. So managing everything around it has some limits, and you have to be very careful with that, especially memory drift is something that happens a lot in industry. But beside these challenges, which again are heavily focused on memory here, there are so many challenges around the RAG chatbot itself. But I assume those issues are already known to you. So managing the chunk size for your documents, having clean documents, having up-to-date documents, these are all the things that you have to take into account if you want to have a good system and a good chatbot. All right, so standard RAG, as I mentioned, is the most important method for us to understand. Let me scroll down a little bit. For instance, RAG with memory, and if I go down, corrective RAG, you can see that some part of their schemas, at least for the next few schemas, are highlighted in green boxes. These green boxes are exactly the same steps that we implemented in our standard RAG. So if you understand standard RAG, you can understand the next techniques and the more advanced techniques much easier. So it starts by the query input. We vectorize our query to perform a vector search on our vector database. So for instance, we can use similarity search for this step. We retrieve some documents. We format all the information, the user's question, the retrieved documents, and also the chat history in case we have a chat history in the next step. And we pass everything to our generator, which is a large language model. And that gives us the response. So this is what we are going to have in this step with the additional memory here. So we have our query input. We have the exact same workflow that I just showed you right here, but let's go through the memory. So we have a memory inside our system. That memory, first, we are going to use it to fetch information after each query input. So in case this is not the first time or the first query of our user, we definitely have some more information about that user. So we are going to provide relevant information along with our query inside our workflow. And finally, when we want to generate the response, we will also update our memory and we will collect the new information from the user and save and store them in our memory. So this is RAG with memory, and this is a standard RAG. With that, let me also go through the project quickly, and then after that, we will see these two methods in action and we will test them together. Okay, so this is the project structure. Again, if you have watched my previous videos, this should be very familiar to you. We have a config folder that contains all the configurations for different RAG techniques that we want to see together. We have a data folder that contains 3 different vector databases. And we have our source folder that contains app.py, which is our Gradio user interface. So this is our Gradio UI. And we have, let me first explain what modules are imported here. So these are all our RAG techniques. If you open RAG techniques folder, you can see all 9 different RAG techniques that we are going to see in the video together. And then we have data processor.py. So for this video, I decided to simulate 3 different vector databases and add them to our project. So these are the content and the information that we store in each one of those vector databases. We have a tech docs database. We have FAQ database. And we have news database. And I'm going to use these 3 databases in the demo to show you how each one of those methods work. And we have load config, which just loads all the configurations that I showed you in this file, in this YAML file right here, and then it distributes all this information across different modules in our project. So I've also mentioned in the README file, but for you to work with the project, there is one important step, which is to create a file called .env, and then add your OpenAI key here. If you don't do it, the project cannot interact with the OpenAI models. Queries.txt is the file that I prepared for the demo section of this video. I'm going to use this file to go through different questions and to explain how each method works. We have the README file. We have references, which contains all the references and the sources that we used to create this video for you. And finally, we have the requirements.txt. These are the libraries that you need if you want to run the project on your system locally. Okay, so let me just quickly show you how you can execute this module. So first, you need an environment, and in that environment, you also need to install all the libraries that are needed for this project. So I already have an environment, and all the libraries are installed. The first thing that you need to do is to run Python source data processor.py. If you execute this one, this module is going to create this chroma_db inside your data folder, and it's going to create 3 different vector databases that I'm going to use for the demo. If you want to use your own documents, you can easily create a vector database from your documents, and you can interact with your documents using any of those techniques. As soon as you have your vector database ready, you can just execute the project by running Python source app.py. It is going to take a few seconds, but then it opens up the Gradio UI for you, and you can start interacting with any of these techniques, and you can also choose any of the vector databases that we just created together. So one quick note, right now the UI is statically pointing to these 3 vector databases. In case you want to add your own vector database, you just need to modify the code a little bit and to just adjust the directory and the path to your vector database, and also probably you want to change the name here. Perfect. So with that, let's go through our first question and let's see how this standard RAG works. With the standard RAG, let's ask a simple question from our tech docs. What is Python? Perfect. So this is what happened. We are starting the standard RAG pipeline. It is using a simple retrieve then generate approach. And it first, in a step 1, it retrieved relevant documents based on the user's question. It retrieved 3 documents using similarity search. And this number is configurable. If you look into config.yaml, you can change this number. And it formatted those 3 documents along with our user question and passed them to the large language model, and eventually our large language model gave us this response. But here, if I ask what was my last question, This method simply just does not have access to any memory, and it cannot answer that simple question. So I'm sorry, but I don't have access to your previous questions. So a quick note here, as you can see right now, what happened is, although my last question was very simple and I really didn't ask a question that needs any documents from the vector database, that pipeline executed the retrieval side and also all the steps that we implemented for our RAG pipeline anyway. So this is exactly why we would need a more advanced technique. So imagine that there is a chatbot that can make a decision in the first step. Do I need to run a vector search on the vector database, or can I answer this specific question just from the memory, or can I answer this question from my personal and from my own knowledge? So that is an agentic chatbot. When we are going through our different methods, I will explain a more complex version of an agentic chatbot, but I just wanted to mention that this is exactly why we would need a more complex system, because this type of system, as you can imagine, this just went through some extra steps, which added to the latency, which also costed, although very small amount of money just for now, because I'm a single user interacting with this database, but anyhow, it costed a small money to interact with the OpenAI embedding model, to interact with the OpenAI GPT model, to come up with a simple answer at the end and eventually it failed. So this is exactly why we need a more advanced technique, and that is what I'm going to explain to you in this video. In the next method, RAG with memory, we are going to go through the same process. So let me just quickly copy this one, run what is Python. So step number 1, retrieving documents with the conversation awareness. Although this is my first question in this chat session, but as you start asking more questions, the chatbot will have access to more information about you. Retrieve 5 documents using context-aware search, prepared 5 docs. These are the number of characters that exist in the retrieved content. And it also tried to retrieve my previous conversation, and it passed everything together to our large language model to generate an answer. Let me ask a follow-up question here. Let's say, what are its main use cases? So this is the answer. Python has a wide range of use cases. So as you can see, the chatbot had access to my previous query, and it was able to prepare an answer and fill the gap and understand what I actually meant by it's right here. So it's easily understood that I'm talking about Python right here. So the only thing that changed in the second query was the injection of what is Python, or the injection of my previous interaction with the chatbot into this next step. So this is RAG with memory, and as you can see, this just gives it a much more natural feeling when you're interacting with it, and it gives your chatbot the power to just start fetching information from the previous conversations and provide you with a much better response. All right, for the last part in explaining these two techniques, I want to also highlight the important parts in their code. So I'm not going to go through each single line in our project because the project is much bigger than I can cover in one single video, but for each method, I will highlight the important parts. So app.py is the top module. This is where we have both our user interface and the class that allows us to interact with our backend. So these are all our techniques. This is RAG Playground, which is the class that I defined that allows us to interact with each one of our methods. And this is where we start and design our Gradio UI. This is our Gradio blocks. And if I go down, you can see that whenever our user submits a query, we call process and update logs. So let's see that function here. So process and update logs gets everything that we have from the UI side. The technique that we want to interact with, the user's message, chat history, database, etc. So here we call getResponse method from our RAG Playground class. Let's go to that method. So this is our class, and this is the method. So all this function does, all this method does, is that it receives all those arguments chat history, user message, techniques that we want to interact with, database, etc. And it just pass those information to the right technique. Here you can see that we are checking which technique was called, and it gets the response from that. So this is all this module does for us. And now let's quickly go back to our standard RAG, and let's see how it was designed. So for this project, I used LangChain to implement all our methods. And as you can see, I'm using ChromaDB for the vector database, and this is the class for a standard RAG. So first, we initialize the OpenAI models, the embedding model, and the large language model. Then we have the retriever. So as you can see, it has access to all databases. So any question that you ask, depending on the question and also which database you want to interact with, the method is able to get the documents and provide the answer to you. Then we just use the user's query to perform the vector search on our vector database. This is where we do that task, get relevant documents. We fetch the documents and we collect them in a list, and we return the list in the end. Then we have the log method. This is for showing all those steps in the UI to you, the extra steps on how each method works. We have process query that essentially does everything for us. So it has a template. So this is the large language model template where you can modify it if you want to add instructions. This is where you can do it. It creates the chain, the RAG chain. It processes the documents, the chat history, the user's query, and combine everything together in order to pass them to the large language model. And essentially, by calling RAG_chain, which is our RAG chain here, .invoke, we can get the response from that chain and we can pass it to our user interface. So this is standard RAG. For standard RAG with memory, you can check conversational RAG. This module is identical to the previous one with one key difference. And as you can imagine, we introduced memory into this RAG method. So these are the two new methods: format conversation history and create contextual query. So here we get, let me open config.yaml. If I go into conversational RAG, there you go. So we have chat history length equal to 5. So we get the previous 5 exchanges between the user and the chatbot, and we also combine them to our input for the large language model. Here we create our query, so we combine the query along with the chat history, and we extract everything that the large language model needs in order to process and give us the response. And in process query, we also modified the template. So right now, the template gets conversation history, relevant context, and the current question. So relevant context is the retrieved documents from our databases, vector databases. This is the conversation history, and this is the user's current question. This is the only difference between this module and the previous one. So I think that was it for our standard RAG and the conversational RAG, or standard RAG with memory. And let's continue to our next technique, which is called corrective RAG. So corrective RAG, or in short, CRAG, is a more vigilant form of retrieval augmented generation that adds a self-check stop before finalizing an answer. So in a standard RAG, whatever documents come back from the retriever are taken as is for answer generation. In corrective RAG, the system evaluates the quality and relevance of the retrieved documents before generating an answer. So think of this method as an AI that doesn't fully trust the first books it grabs from the library. It quickly skims them to see if they really answer the question. If not, it corrects the course by filtering out irrelevant data, searching additional sources, or rephrasing the query. So as you can imagine, this method is trying to solve a critical challenge in RAG pipelines. So one of the most important aspects of a RAG pipeline is accuracy. And if you have a complex database, or if the user's question and query that you might get from your users are not very clear and they may be vague, this method is going to solve that problem by double-checking the content, making sure that they contain the information that the user is looking for before providing the user with an answer. So Architecture summary, we have the query, we have the retriever. This is the newest step, evaluator. And then we also have optional re-retrieval before generator. So these two together would give you a full corrective RAG. And in the pipeline, we have them both. But you can also just add an evaluator in order to trim and, let's say, clean up the information before passing them to the final large language model, which is our generator. That is another way that you can implement this method. Let's go through some of the use cases. Corrective RAG is especially valuable when accuracy is critical or the knowledge base may be incomplete or inconsistent. So some of the use cases are enterprise Q&A with limited data. If an internal wiki lacks the right answer, CRAG can automatically broaden the search. For instance, it can query the web or a larger database instead of giving a wrong or incomplete response. Legal or medical assistance. These systems can't afford to rely on outdated or irrelevant info. CRAG ensures that sources truly match the query, and if not, it retrieves up-to-date guidelines or research papers. Fact-checking systems. A fact-checking bot can retrieve related information, verify HPs, and discard unreliable sources, effectively correcting any misleading retrievals. So these are some of the use cases that you can think of, but of course there are so many other use cases that you can implement this technique for. So let's also go through an example scenario. Imagine asking a research assistant about a topic where internal data is limited. So user's question: what were the sales figure for our product Z in Q4 2025? So the AI searches internal databases and finds document about product Z sales, but they only cover 2024 or are partial drafts. Step 2, relevance check. The evaluator scans these docs and realizes that they don't confidently answer the question. It assigns low relevance scores to all retrieved documents. Step 3, corrective action. Since results fall below the relevance threshold, CRAG rewrites the query, product Z sales Q4 2025 company name, and searches external sources such as financial databases or the web. Step number 4, new information. A press release from January 2026 is found with the Q4 2025 sales data. Step 5, knowledge refinement. The AI extracts key points. Q4 2025 sales were $5 million, a 10% increase year over year. It filters out irrelevant info using a decompose-recompose strategy. Step number 6, answer generation. Finally, the language model generates a precise answer. Product Z achieved sales of $5 million in Q4 2025, a 10% increase over the previous year, citing the press release as the verified source. So what was the result? The result was, with CRAG, we can address one of the shortcomings of a standard RAG. So a standard RAG might have given an incomplete or incorrect guess because the database did not contain the right information. But CRAG identified the data gap, researched for getting the right answer, and corrected the result. What are the challenges here? So the evaluator cost is an additional cost in our RAG pipeline. Running a large language model to grade every retrieval increases latency and token usage. Threshold tuning is our second challenge. Finding the right relevance cutoff is difficult. Too strict misses info, and too loose allows noise. So as you can imagine, based on that threshold, your system is going to make a decision whether to use the documents that were retrieved from the vector database, or, for instance, to make or to perform a web search. So that threshold by itself needs to be fine-tuned and needs to be adjusted based on your needs. And that adds to the challenges. The third challenge is external search trust. And for that, fallback searches must validate source reliability to prevent misinformation. This is another layer of complexity in your system. And finally, context drift. Multiple correction loops can add noise if not properly filtered. Some notes here. Corrective-like RAG flows appear in Anthropic's constitutional AI and OpenAI's self-grading retrieval systems, where models assess their own sources for factual confidence. Frameworks like LangChain's evaluator module and Llama Index feedback node enable these self-corrective loops in production. So in our project, we are using LangChain, but almost all the frameworks now provide you with some sort of self-corrective method. In essence, CRAG acts like a safety net, reducing the risk of hallucinations or incomplete answers by verifying and refining retrieved knowledge. All right, so let's also go through the schema. As I mentioned before, the sections that are highlighted in green are exactly the same process that we implemented for our standard RAG. So let's go through it and let's see the difference. We have the query input, we vectorize the query, we perform a vector search on our vector database, we retrieve top K documents, then we have an extra large language model compared to our previous methods that performs the evaluation for us. So it evaluates the retrieved document for query relevance. Then here we have the decision gate. Here is the point that we make a decision based on that threshold. If the documents are sufficient, we go through the normal pipeline as before. If the documents are not sufficient, they are insufficient, we trigger the correction method. We reformulate our query, we perform an external web search, and then we pass the result to a large language model to give us the final answer. So in this system, 3 large language models are involved. The first one is to evaluate the retrieved documents for query relevance. The second one is to generate the response, and we have it in both paths. And the third one, which gets triggered in case there is not enough information in our documents, is to reformulate our query. So for each individual query, there are at least 2 large language models that are getting triggered in this system. Okay, now let's go through our module, Corrective RAG, and after that, we will pass some queries and we will see the performance of this RAG method together. So here, beside the retrievers, we also have set up graders. So let's go through the new sections and let's see what was added to this module. We have set up graders, which again, we are using a class grade documents from LangChain, and we create a large language model for grading the documents. So this is our LLM with a structured output grade documents. This is the system prompt for our grader. So this is how we create a grader chain, .grader chain, and this is for evaluating the documents. Then we have rewrite system prompt. So this is the system prompt for our third large language model. Again, we create the chain and we bind our prompt with the large language model and also the string output parser from LangChain. This is again the same function that we use to print the logs in the UI. We also have a web search. This is also new. Just keep that in mind that right now, just for demonstration purposes, we are limiting the number of inputs that we pass to our large language model. It is hard-coded here that we only get the first 50 characters. Then we have grade documents. So we use our .grader chain to go through each retrieved document and give it a score. By the time that we want to execute this function, we have already received our retrieved documents. So here we loop over each document, we invoke .grader, and we assign a score to each individual document. Then, based on the score for each document, we decide whether to keep that document or not, or we decide whether that document was relevant or not. In case the number of relevant documents is equal to 0, we are going to perform a web search. So as you can see, no relevant documents found, web search required. In case relevance ratio is less than 0.5, we are going to suggest the system that web search is recommended. So we have some relevant information inside our documents, but it's also good to perform a web search to get additional information. And finally, in case we have multiple relevant documents, the decision would be sufficient relevant documents, no web search is needed. So we have, again, process query that runs the full pipeline for our corrective RAG. The only difference here is that we are going to implement those extra steps in our pipeline. So as you can see, we have our retriever, we have our grade documents, we have the web search process, and in case we perform a web search, we are going to get the response process the response, pass it to our final large language model to give us the final answer. So this is the full RAG chain for corrective RAG. So now let's go to our chatbot and let's start interacting with our corrective RAG. So corrective RAG, CRAG, and let's go through some of the questions. So here I want to test all the three scenarios. So if I start with a simple question that I know our document contains enough information for this one. So what is Python programming? In tech docs, and the model should be able, or the pipeline should be able to give us the proper answer. Well, by the look of it, I think our corrective RAG decided to also perform a web search. Let's go through all the steps together because it is giving us an answer, but based on what I'm looking at right now, I think it also performed a web search, which is actually an interesting case that I want to discuss with you. So let's see here. Step number 1, initial document retrieval from local database. Then it retrieved 3 documents. Then we executed our doc grading system. Then the first one was relevant, the second one was not relevant, and the third one was not relevant. So yes, it was definitely received the lowest score, and it went for a web search here. So as you can see, document grading was 1 out of 3, which is 33.3%. Then we entered in the correction process. Insufficient relevant documents, applying corrective measures. So query transformation, rewriting query for better retrieval. What is Python programming? What are the key concepts and features of Python? And then it used web search, which is using OpenAI's web search tool. Then it retrieved 456 characters from the web, and we combined local documents plus web search result and passed it to our final model. So this is interesting because my initial thought on this question was that we are going to get sufficient data from the vector database. And actually, we have enough information on the vector database. But it is a great example because it really depends on how our grading large language model is going to make its decision. So as you know, large language models are non-deterministic, which means that their response might change over time. And also the retrieved documents that we pass to a large language model might have changed. So something in the system changed based on my previous tests that made our system to go and perform a web search for this question, which is again an interesting point. And this is exactly one of the challenges that I mentioned in the documentation, that you have to come up with the right threshold and you have to fine-tune your system, adjust your system to make sure that it is performing as expected. Let's continue and let's go to the next question. So let's ask another question that I know we have enough information in our database. What is your return policy from FAQ data? Our return policy allows for return within 30 days of purchase. So let's see the process here. We got the retrieved data, number of retrieved documents 3. Then it kept 2 out of 3 retrieved documents. So the score was 66%, which was sufficient for our system, and we didn't go through any web search for that. So this was what I wanted to show you with the previous question. But since in our previous question, the performance was different than I expected, I decided to also pass a second question, which I knew for sure that we have the information in our database. Okay, so let's continue and let's ask another question that is going to trigger. So actually, since we saw 2 scenarios out of 3, let me ask the final question that triggers the full web search. So current cybersecurity threats in 2024. We don't have any information for this query. Okay, we got the response. Let's see the response together. So as of 2024, the landscape of cybersecurity threats continues to evolve, and it gave us a full answer. Let's go through the process here. Step 1, initial documents retrieval. We retrieved 3 documents. All of them were not relevant. So as I mentioned, this was the third scenario. So our relevance score or relevancy score was 0%. And for this one, we performed a web search. We provided the web search result to our final large language model, and it generated the response for us. We saw all the 3 scenarios for corrective RAG. And as you can see, this is a very powerful method for verifying the content and the documents that you retrieve from your vector database. All right, so let's go through our next RAG method, which is called adaptive RAG. Adaptive RAG introduces flexibility in how much retrieval the AI performs, depending on the complexity of the question. So if you remember what I mentioned when we were going through the demo for naive RAG and RAG with memory, and the fact that that system was going through the same process regardless of the complexity of the query, this method is how we can solve that problem. In a traditional RAG or naive RAG, the system retrieves a fixed number of documents regardless of query difficulty. So whether we ask, what is 2 + 2, or explain the impact of climate policies on European economies, the system goes through the same process. This fixed behavior can be inefficient. Simple questions don't need deep retrieval, and complex ones might need multiple rounds of research. Adaptive RAG first analyzes the query's difficulty, then chooses a retrieval strategy. So in our system, we have 3 different strategies. First, no retrieval, so the model uses its own knowledge. Then single-step retrieval, just like what we did for our standard RAG and RAG with memory, or multi-step retrievals. And our system dynamically adapts to the situation. In short, it behaves like a smart researcher. Easy questions answer directly or with minimal lookup. Hard questions perform deeper iterative retrieval before generating an answer. Okay, so here we start by a query, then the newest step that we add here is complexity analyzer. And then we have a conditional path. Depending on the conditional path, we may either point to our standard RAG method, or we may go through a more complex structure with multi-step iterative retrieval, and then we pass the response to the generator. So let's go through some of the use cases. Adaptive approach is ideal for mixed query environment, when user questions vary from trivial to complex. So the first use case is general QA systems, search engines, or AI assistants. User queries can vary widely in depth. Adaptive RAG can skip unnecessary retrieval for trivia, saving time plus tokens, or it can use multi-hop reasoning for complex analytical queries, improving accuracy. The next use case is customer support bots. Some questions are easy, what is your return policy? While others are layered. My account was overcharged across 2 billing cycles. How do I fix this? So adaptive RAG can answer both efficiently. It can perform a quick recall for simple queries, or it can perform a deeper retrieval for multi-part cases. Educational tutors. In tutoring systems, simple factual questions can be answered directly. But on the other hand, open-ended or multi-hop ones, like how does photosynthesis lead to plant growth, or why does it matter for agriculture, triggers multiple retrievals and synthesis. All right, so now let's go through an example scenario. Consider an AI assistant handling both simple and complex queries. Question A, what is the capital of France? Complexity analysis recognized as a straightforward factoid. Strategy, no retrieval needed. The AI already knows the answer. Answer, the capital of France is Paris. So it is fast and efficient. It skips unnecessary document search. Essentially, it saves you both cost and time. Question B, what was or who was the mother of the inventor of telephone? Complexity analysis, multi-hop reasoning, involves 2 steps. Identify the inventor, and then identify the inventor's mother. Strategy, multi-step retrieval. Step 1, we search for inventor of telephone, and we find the answer, Alexander Graham Bell. And in the second step, we go for the second query, Alexander Graham Bell's mother's name, and we find the mother's name. So if an intermediate fact was already known, the AI could skip a step, and it could adapt dynamically at each point. So as you can imagine, having this feature in our RAG system is not going to come without any technical challenges. So the first challenge is complexity estimation accuracy. Misclassifying a query can waste resources or miss depth. So it can go, or it can happen in two different directions. We send a simple query and our classifier decides that this is a complex query. So in that case, we are going to have a higher cost and a higher latency for a question that could have been answered much easier. Or the other way around, that we send a complex query and our system decides that this is a simple query and I can even answer this using my own knowledge. So in that case, there is a chance that we get hallucination or we get a response that is not fully accurate or it's not complete. The second challenge is dynamic latency. Multi-step retrieval causes variable response time. So the users should be aware that this can happen. If you chat with ChatGPT right now, this is exactly what you see. So when you ask a question that is a little bit more complex, it starts to think. But if you ask a very simple and straightforward question, it immediately give you the response. Cost versus benefit, which is a very important factor in this system because we have some new layers compared to our standard RAG. So adaptive logic adds computational overhead, and for that we need to first justify our cost and savings and make sure that this is the right approach that we want to implement. And finally, state management. So this is the technical challenge. Multi-hop steps require maintaining context and handling intermediate errors. Just a quick note, frameworks like LangGraph and semantic router support adaptive routing, enabling light or heavy retrieval paths depending on the query. And we are going to use LangChain for our project. So here's the schema for adaptive RAG. Again, the green sections are the parts that we already saw and implemented for our standard RAG. So we have our query. Actually, this is where we start. So we have our query input. Then we have query classification hub. So this is where a large language model decides whether this query is simple or complex or what strategy we need to proceed to get the answer for this question. If it is a simple query, we go through our standard pipeline. If it is a complex query, we perform multi-retrieval and we go through different steps: initial retrieval, reformulate search query, secondary retrieval, etc. So you can implement as many retrieval steps as you want in your system. Or if it is a vague query, in that case, we first write or rewrite our query, we clarify and expand query intent, and we enhance the similarity search or our vector search on our database. And in any of those cases, we are going to pass that to our final large language model to get the answer to us and to get us the response. So as you can see, multiple large language models are involved in this system. In the fastest scenario, there are two large language models, one for classifying our query and one for generating the response. But as the query gets more complex, there are more LLMs involved. We have an LLM for reformulating the search query, and depending on how many times you want to do it and how many loops you want to go through to get to the final answer, the LLM calls will increase. Or in this case, for instance, to rewrite the query, we are going to use another large language model. So depending on the path that the system is going to take, the number of large language models that are involved is going to change, and that is another layer of complexity that you have to be able to manage. And you also need to, again, as I mentioned right here, you have to make sure that the cost and benefit of the system makes sense, and this is the method that you want to implement for your project. All right, so now let's go through the differences between adaptive RAG and the previous techniques that we saw together. So we import the libraries that we need, we create a class called adaptive RAG, and we initialize the embedding model, OpenAI, and the methods that we need. So this is exactly identical as Corrective RAG, but the content of setup graders is different here. Setup retrievers, same as before, we create a retriever for each individual database. And in setup graders, we will use LangChain's built-in functions and classes to create our router, document grader, and rewriter methods. So we use router query class, and we define three different strategies: standard, multi-retrieval, and rewrite. So let's go through the description. Choose retrieval strategy: standard for simple queries, multi-retrieval for complex queries, rewrite for unclear queries. Then we have grade documents, And the description is documents are relevant to the question yes or no. So we are going to score the documents based on their relevancy. We have the large language model for our router. Again, we are using built-in methods in LangChain. We have the large language model for our grader, and this is the system prompt for our router. You can also modify the system prompt, but the available strategies that we want to pass to the model are exactly the ones that we saw together: standard, multi-retrieval, and rewrite. Just keep it in mind that this description is just for this class, for you to understand what happens inside this class, but this is what the model sees and uses to make a decision. Then we create the chain for our router. This is the system prompt for our grading system. Then we create a chain for our dog grader, and this is the system prompt for our rewrite method, and we create a chain for that as well. Log is exactly similar to the previous methods. We have route query. So when we call the router, this function is called, and this function invokes our query router chain. And then we also have the grade documents method that, again, just like the previous one, when we call grader documents, dot grader, we call this function, and this one invokes dot grader, and it gives us the result. And we have rewrite query. So this one invokes query rewriter and gives us the result. Then, depending on how we want to interact with the database, so we have a retriever that we created here. So this is just this retriever just allows us to interact with the database. But we have two different strategies to interact with our databases. One of them is standard retrieval, in which we just simply query our database, get the results, and pass them to the large language model. Or we want to perform a multi-retrieval. So as I mentioned earlier, this function can be defined based on the strategy that you want to implement and you want to utilize. So for instance, right here, I decided to perform two different searches on the same database. So I have a retriever that points to the selected database in the chatbot. First, we query that database using our original query, and then we query that database using an alternative query. And then we combine the results and we pass them to our large language model. But you can go through the same database multiple times or go through different databases, depending on how you want to implement this function. Then we have process query, in which we just wrap everything that we defined so far in this class, and we create our full pipeline. So now let's go through the chatbot, and let's see how our adaptive RAG works. So let me also open my questions. Now let's ask a separate question and trigger each one of those methods that we implemented for our adaptive RAG. So the first one is a very straightforward question. So the pipeline should use the standard route and give us the answer for this one. Here's the answer to our question, and now let's go through the logs and let's see what happened behind the scene. So in the first step, our router decided to go with a standard retrieval, single similarity search. The question was simple enough to trigger this method in our pipeline. We retrieved 3 documents using this method, and then we grade those documents. Document number 1 was relevant. Document number 2 and document number 3, they were not relevant. So we filter out these 2 documents. We only pass the relevant document to our final large language model to give us the response. This is exactly what we expected for this question, and the pipeline gave us the answer for that. Now let's go through the next question, and let's trigger multi-retrieval. So for this one, I just want to ask for a comparison. I want the pipeline to compare Docker containers versus Kubernetes. All right, so we got the answer for our question. Let's just quickly check the answer. So we have the first section for Docker containers. In the next part, it explains Kubernetes orchestration, and also it performs a comparison and it gives us the full answer. So now let's go through the logs and let's also see what happened. So in the first step, our router decided to go with multi-retrieval. So it checked the query, and it decided that this is a complex query, and we are going to go with multi-step retrieval. In the next step, we expand our search. So this is exactly what I showed you in our function. So we perform the first vector search, and we retrieve 3 documents. We also perform the alternative vector search, the second vector search that we implemented in our pipeline, and we get 2 additional documents. And just to show you where that comes from, if I open my config, go to adaptive RAG, you can see that multi-retrieval first top K is 3 and multi-retrieval second top K is 2. So this is exactly what happened here. In the first step, we retrieved 3 documents. In the second step, we retrieved 2 additional documents. Then we checked all those five documents, and we found 3 unique documents after the duplication. So we remove the duplicate documents, and we only keep the unique ones. And again, we start to check if the documents are relevant or not. The first document is relevant. The second document is relevant. Third document is not relevant. So we pass these 2 documents, and the large language model prepared the response based on those 2 documents, and it gives us this response right here. It compared Docker containers with Kubernetes orchestration. For the third question, we want to ask something that is vague. So there is a note here. This method right here, adaptive RAG, does not have a memory in it. Because if I had a memory and I would ask something like, how does it work? Instead of triggering rewriter, the pipeline would see the previous conversation, and it would replace this vague question with something relevant to the previous conversation. But I just wanted to show you, even if the model does not have any context or the pipeline does not have any context about what happened in the chat session, how that rewriter would come into the game. But the important note here is that when you want to implement this pipeline for your project, you definitely want to implement a memory for it, and you need to change the system prompt for the rewriter and also the system prompt for the router to explain in which scenarios you want to trigger rewriter. So right now, since I wanted to keep it simple, I just removed the memory from the pipeline, and if we ask a question just like this, the model is going to give us the answer and rewrite that question with something that is not relevant to our previous conversation. So let's check the answer together. Neural networks work by simulating the way biological brains process information. So it decided to search for how neural networks work. Let's go through the log and let's see what happened behind the scene. So strategy, the router decided to trigger our rewriter path. Then we improve unclear query for better retrieval. Original query was, how does it work? The new query is, what does the process or mechanism behind a specific topic or subject? But this was replaced by what the model came up with, which is clearly the neural network. So I forgot to change the log here, but it was definitely about the neural networks. Then in step number 1, we have the standard retrieval. We go through the vector search, retrieve the documents. We check the relevancy of our documents. 3 out of 3 documents were relevant. We pass all the documents to our large language model to generate the final response for us. So again, this was just for demonstration purpose. I didn't add memory to this pipeline, and in case you want to implement it for your project, it needs a little bit of modification. You want to play around with the system prompt for the router. You want to play around with the system prompt for the rewriter to get the best performance out of this method. Now let's go through our next method, which is called self-RAG. Self-RAG also tries to solve the original issue that I raised in a standard RAG, but from a different perspective. Self-RAG gives an AI system a kind of introspective ability, the capacity to question its own confidence, decide when to retrieve information, and verify its own answers. In a standard RAG, the AI retrieves a fixed number of documents every time, whether needed or not, and never questions the alignment between its answers and the sources. Self-RAG changes this. It enables the model to, first, decide if and when retrieval is needed. Then, critique its own draft answer before finalizing. And third, verify that each claim is supported by evidence. So this is achieved through special reflection tokens that are is relevant and is supported during prompting or fine-tuning. These allow the AI to think, am I sure about this? Maybe I should double check. Or does my answer align with the sources I retrieved or not? So from a high-level perspective, this is what self-RAG does, but when we go through the schema, you will understand it in a much better depth, and you will understand all the steps. So we start by a query. We have a plan. In that plan, we have to decide whether we need retrieval or we need more retrieval. In case we need retrieval, we perform targeted retrieval. We also draft a response. We check that response and see if it is supported by the content that we retrieve from our vector search. If we are satisfied, we finalize the response. If we are not, we perform more retrieval and we fetch more documents from our different sources. Let's go through some of the use cases. So this method is particularly powerful when factual reliability and dynamic retrieval are crucial. The first scenario is knowledge assistance in specialized domains. In areas like medicine or finance, the model may know basic facts, but must ensure accuracy. Self-RAG fetches domain-specific references only when needed and verifies its advice, which then leads to less hallucination. The next scenario is long-form generative writing. You can think of it as reports and essays. For extended outputs, self-RAG can periodically verify claims as it writes. It retrieves supporting data per section, checks consistency, and even attaches citation for transparency. And the final scenario here is interactive chatbots with unpredictable queries. A self-reflective chatbot can handle simple questions confidently, can retrieve extra info for unusual or complex ones, and can critique its own answers, post-generation, and correct if necessary. So here I have an example scenario. Imagine an AI answering user questions about history. Some of it knows, and about the other parts, it might have questions and it might need supporting documents. So the user question is, did Benjamin Franklin really propose daylight saving time? Internal reasoning. The AI recalls that Franklin once mentioned adjusting sleep schedules, but isn't sure if that counts as formally proposing daylight saving time or not. In the self-reflecting section, or when self-reflection is triggered, we use a token called isRel, or is retrieval relevant here, which allows the model to understand whether it's uncertain about that response and it needs more supporting documents, or it is confident. So in the next step, we have adaptive retrieval. So our model searches for Benjamin Franklin daylight saving time letter and finds a reference. Franklin wrote a satirical essay in 1784 suggesting people wake earlier to save candles. The draft answer. Benjamin Franklin did mention the idea of adjusting clocks to save candlelight, but he didn't formally propose modern daylight saving time. Self-critique. So here we use our second token. Is supported? Is the answer supported? The model reviews its draft against the source, it confirms the alignment, and it sees that Franklin's mention was indeed satirical, not a policy proposal, and it finalizes the response just like this final response right here. So this is an example workflow of self-reflective or self-RAG. What are the challenges for this method? The first one, as you can imagine, is latency and token overhead. We have two extra steps here, reflection and verification. So managing these two steps is very important, and also we have to take into account the time that they need to perform, and also the token overhead, because we are going to go through different loops, fetch different information, which gives us a lot of context that we have to be able to manage and compress if needed. Over or under retrieval. In this pipeline, there is a key decision that needs to be made by our large language model, one of our large language models. We have to fine-tune that step very carefully to avoid too many or too few retrievals. Then we have granularity of checks, and by that I mean whole answer checks are coarse, and as you can imagine, on the other side, span level checks improve precision, but they are more complex and they are harder to implement. Consistency versus correction. Self-edits may shift tone or logic. This is a fact, and you have to be aware of it in this system. But a structured revision templates can help mitigating this problem. Citation quality is our next challenge, but we can ensure claim to source alignment using entailment checks or rescoring. And finally, just like any other technique that we saw today, cost control is another factor that we have to take into account. So here, the suggestions are apply guardrails, limit reflections, top-care retrievals, and compress sources when scaling. And these are some notes for implementation. Use uncertainty signals, log prop thresholds, entropy, or I'm not sure prompts to trigger retrieval dynamically. Prefer targeted retrieval per claim or span, not large bulk retrievals. It is more precise and cheaper. Then add an entailment or QA over source step that, for instance, says, does source S support claim C before you publish a response? Next, log reflection events, why retrieval occurred, what changed after verification, and these type of questions to build trust. And also, it will make it easier for you to debug the whole system. And for long outputs, follow a section-wise workflow. Draft, retrieve, verify, lock this section, do the same for the next one, and eventually compile final output. Okay, so now let's go through the schema. And as I mentioned, here everything will become very clear for you. The self-RAG pipeline that I implemented for you here works just like this. We have our query input, we embed our query, we perform a similarity search, and we retrieve some documents. So this part is, I didn't highlight them in green boxes anymore, but as you can imagine, this part is exactly following the same process as our standard RAG. But here is when everything changes. We have a self-reflection step. So in this step, we grade documents for relevancy and quality. Then we have a quality gate, which filters those documents. So we use the quality filtered documents to generate a response. This is our draft response. We check our draft, and we decide whether that draft is the final response or we still need more context and more information to come up with an accurate response. In case we need more information, we go back to our loop, we rewrite our query, we perform another search, and we go through the process again. We go through this process until either of these two things happen. For one, we get to a point that the information that we have is sufficient, and we are confident that the response is accurate, or we hit the maximum retries threshold. In that case, we accept available relevant documents, and we generate the final response, and we show that response to our user. So this is the full workflow of our self-RAG, and this is exactly what I implemented for you in our project today. So let me open self-RAG, and let's go through this module together. This module has a lot in common with the previous pipeline, so I will just focus on the changes here. So let's look at setup graders method. We have grade documents class from LangChain, and the description is documents are relevant to the question yes or no. So this is what we want to do for grading documents. We saw it before as well. We have grade hallucination. So this is a binary score for checking whether hallucination exists in the final response or not. So this is the class that we want to use. And we have grade answer, which is, as you can imagine, a class that checks whether the answer addresses the question or not. So we have our dog grader, just like before. We have hallucination grader, LLM. This is new here. We have answer grader, LLM, again, for this new technique. We have dog grader system prompt. So here we check if the document contains any concepts, keywords, or topics related to the question, grade it as relevant. And if it doesn't contain relevant information, you can mark it as irrelevant. And we have dog grader prompt, so this is how we create the chain for that. We have our hallucination system prompt. You are a grader assessing whether an LLM generation is grounded in or supported by retrieved facts. So it gives us a yes or no in the output. This is, again, the large language model for hallucination system, and this is our chain. And finally, we have our answer system prompt. So you are a grader assessing whether an answer addresses or resolves a question. In the output, it gives us a yes or no, and this is our chain. And finally, we have rewrite system. Rewrite system, just like before, you're a question rewriter that converts an input question to a better version optimized for vector store retrieval. Look at the input and reason about the underlying semantic or intent meaning, and then it rewrites the query, and we can use it in our loop. So this was the changes in setup graders. In the next step, we start to add functions that utilizes each one of those methods. So we have grade documents that invokes our dog grader and gives us the output. We have generate response that calls the final large language model to generate the response for us, and this is the system prompt. We have reflect on generation that checks two things here. So first, it invokes hallucination grader, and in the next step, we also invoke answer grader. So in case hallucination does not exist in the answer, we also check the answer quality based on the content and verify whether our answer has the right information in it or not. And we wrap everything into our process query function just like before, and we create the pipeline. So this is the self-RAG module. Let's go through the chatbot and let's ask a few questions from our self-RAG technique. So the first question that I want to ask is, how do APIs work with different database systems in software development? As you can see, it's taking much longer than the previous techniques. This is exactly showing us what I mentioned in the challenges about the latency of this technique. And here's the response. APIs communicate with different types of database systems through various mechanisms. And it gave us the full response in the following. I'm not going to go through it, but let's go through the logs and let's see what happened behind the scene. Step number 1, we performed the initial retrieval. We retrieved 3 documents from our TechDocs database, vector database. We then score and grade those 3 documents. The first document was relevant. Document number 2 and document number 3, they were not relevant. So what happens here is that self-reflection check the result, and it realizes that too many documents were failed, and we need to trigger query rewrite. In the next step, we trigger query rewrite. It generates a new query for us. So this is the beginning of that query. What are the key mechanisms by which APIs interacts with something? You can see the full query if you want to print it in the logs. For simplicity, I just print the first section of the query here. In the next step, we perform another retrieval using the new query. So let's see what happens here. 3 documents were retrieved. Again, document number 1 is relevant. Document number 2 and 3 are not relevant. So we go through the same process. Self-reflection is going to trigger our rewriter. Our rewriter comes up with a new query. What are the primary mechanisms through which APIs communicate, etc.? So we use the third query or the second query that we received from our rewriter chain, and we perform another vector search on our database. Again, we retrieve 3 documents. This time, 2 out of 3 documents were relevant. So self-reflection, this time, is satisfied with the output, and it says sufficient documents passed. We proceed with generation. After self-reflection, we go and pass all those documents to our large language model to generate the response. So we generate the response, but we also check the response for hallucination and for quality. Evaluating generated response quality, hallucination check passed, response is grounded in facts, and also the quality of the response itself, question relevance check passed. Response addresses the question. And at the end, the pipeline prepares the answer and shows the answer to the user, just like what we saw on the left side. So this is one example for our self-RAG method. Let's ask another example. So this time, I want to ask a question from a different database, FAQ database, and the question is, what happens if my item is damaged during shipping and I need to return it? Okay, we got the answer. This time was faster. And if you receive a damaged item during shipping, follow these steps to ensure a successful return. So the pipeline was successful. Now let's go through the logs again. Step number 1, initial document retrieval. We retrieved 3 documents. We grade those 3 documents. 1 was relevant, 2 were not relevant. So self-reflection is going to call for a rewrite. Then we get this new prompt, which is what is the process for returning a damaged item received, etc. We perform a vector search using this new query. We get 3 documents. This time, 2 out of 3 retrieved documents were relevant. So as you can imagine, self-reflection is going to pass this step, and we are going to generate a response. The response was generated. We check for hallucination. Hallucination passed. There was no hallucination in the response, and also question relevance passed. And after that step, again, we finalize the response and we show it to our user. Let's ask one final question, and let's see how the pipeline performs on this one. What are recent advances in AI and healthcare technology? Let me change the database to news articles. We received our response, and if we go through the logs, we can see that this is almost identical to the first case, except the fact that our pipeline could never retrieve more than 1 relevant document for that query. So this is the first attempt that was failed, and we called our rewriter. This is the second attempt that was failed again. And this is the third attempt. So what happened here is that we reached to the maximum threshold that we defined for our loop. We eventually accepted the available relevant documents. We passed it to our large language model to generate the final response. So this is another behavior of our pipeline. Now let's go through our next technique, which is called Fusion RAG. Fusion RAG focuses on combining information from multiple sources or queries to produce a more complete and reliable answer. In a standard RAG, the system issues one query to a single knowledge base, for example, a vector database, and relies on whatever it retrieves. Fusion RAG asks, why not retrieve in multiple ways and merge the results? There are two main fusion types. Retrieval fusion, that runs multiple searches on different sources or with varied keywords and aggregate the retrieved documents. And we also have generation fusion, in which we make the model to reason over multiple information streams separately and blend them during answer generation. From a high level, we have a query, we perform multi-retrieval branches like different queries, sources, retrievers, etc. And we combine the information that we retrieve and we provide the final response based on the combined and aggregated data. Let's go through some of the use cases. So Fusion RAG excels when knowledge is distributed, siloed, or multifaceted. The first scenario is enterprise systems with multiple data stores. So a company might store data in PDFs, SQL databases, and FAQs. Fusion RAG can query all simultaneously. For example, vector search on docs, SQL query, plus web page crawl, then combine them for a comprehensive answer. There is one important note here. So when you read this sentence and this use case, there are two different things that might cross your mind. The first one is implementing a complete RAG pipeline, a single RAG pipeline that searches multiple databases as we are explaining it right here, and it performs a vector search on documents, it performs RAG on tabular databases, and also it performs a web page crawl. Or you might think of having a system with multiple agents, such as a RAG agent that performs vector search for you on documents, a SQL agent that performs SQL queries on your SQL databases, and even a web page crawler agent. So that is a multi-agent system, and these are two separate things. So that by itself is another type of project that you can implement for yourself. But what I'm explaining here is a pure RAG pipeline. So I have a video in which I explained how you can interact with your tabular databases, either using a SQL agent or using RAG pipelines. There are two different ways, at least two different ways that you can prepare your data and interact with it. So here, when I'm talking about SQL query, I don't mean a SQL agent, but I mean literally preparing those tabular data in text format that you can perform vector search on them. But again, you can also implement multi-agent systems and you can achieve a much more powerful output than what we are describing right here. Next scenario is complex questions requiring broad coverage. Questions like compare the benefits of solar versus wind energy, which involves multiple subtopics. Fusion RAG can retrieve documents focused on solar and wind separately, then merge the findings for a balanced comparison. And finally, hybrid search engines. Modern search stacks often blend keyword and neural retrieval. Fusion RAG fuses results from both, improving recall and giving the generator a richer and more accurate context. Again, if you want to implement the search engine by yourself, like if you want to simulate a small search engine in your backend, that might end up being a multi-agent system behind the scene. But here what we mean is just to use the output of those search engines that are available out there and combine the results and then provide the final response based on the aggregated data. And finally, multilingual or multimodal knowledge. Fusion RAG can even combine results across languages or modalities, for example, text or images, to provide unified insights. While multimodal RAG is a category of its own, the fusion principle, and by that I mean integrating diverse data streams together, is shared among both of them. Example scenario, what are the differences between the iPhone 14 and iPhone 15? So we create two queries, iPhone 14 versus 15 camera and performance differences, and iPhone 15 new features over iPhone 14 specifications. Then we perform different searches. Query A, Tech review databases find detailed comparisons of camera and performance. Query B, Apple's official spec sheets, which then gives us precise hardware specs. And we also may perform a web keyword search that gathers forum summaries or review highlights. Fusion of results. The system aggregates all retrieved info, perhaps using reciprocal rank fusion or weighted averaging, producing a ranked merged document set. This is another important step. So there are different ways that you can rank documents and choose which output you want to filter and pass to your next step. You can even use a large language model in the process. But there are so many different ways that you can do it, and there are so many different techniques that have been introduced. This is just an example. And finally, we get the final response based on all these steps that we went through. So what are the challenges of this system? Latency and token overhead, just like before. So multiple retrievers here, which will end up with a higher compute cost. So we can use parallelization or context compression to tackle some of those issues. The next problem is balancing sources. Some sources may dominate the fusion. So we can use weighting systems, and by weighting them by relevance or scores or trust. The next problem is fusion complexity. Designing the right aggregation methods, such as RF, rank voting, vector merging, etc., affects performance. Cross-source conflicts. Sources may contradict each other. The generator must resolve or flag them. And finally, scaling cost. Running many retrievers and long context can be expensive. We can optimize our top K value and summarization steps. And some notes here. So use diverse retrievers, keyword embedding, structured database queries to maximize coverage. Apply fusion algorithms like RF or weighted BM25 plus vector scores for balanced aggregation. Keep a metadata trace, source IDs, scores, query paths for auditing and explainability. For multi-step retrieval, cache partial results to reduce latency. Use chunk summarization or re-ranking to control context size before passing to the large language model. So these are just some of the notes that I'd recommend you for implementation. Let's go through the schema together here. As we saw, when we get a query input, we pass it to our multi-perspective search generation. So the task of this node is to generate different queries for different resources. So imagine we have query 1, query 2, and query 3. We use query 1, for instance, to perform a search on a vector database. We use our second query for a web search, etc. We collect the information from each one of those searches. So imagine 5 documents from each. Then we combine and deduplicate results. So we just make sure that there are no overlaps and everything is unique. Then we merge all search results and identify unique documents, as I mentioned. We rank documents based on appearance across multiple search approaches. So this ranking system right here, it is super important. There are so many different ways that you can rank them, but the most important thing is to come up with the most relevant and informative documents that you can, so you can pass them to the large language model. We create a comprehensive result and we show it to our user. So let's go through our code and let's see how this method works. As you know, the structure of the module is exactly identical to our previous techniques. So let me just go through the changes. So we have a large language model for our query generation, and we have a large language model for our answer generation, and we have a method called setup generators. So here we have 2 system prompts. The first one is for query generation, and the second one is for answer generation. So let's quickly go through this one. You are an expert at creating diverse search queries. Your goal is to generate queries that will retrieve different types of relevant information. Then we pass the original query, and we tell the model, create 3 alternative queries that approach this topic from very different angles. Query strategies to use. Definitional. Focus on what is, or basic concepts or definitions. Relational. Focus on connections, relationships, or comparisons. Practical. Focus on applications, examples, or implementation details. And finally, contextual. Focus on broader context, history, or implications. make each query significantly different in keywords used, scope, perspective, and information type sought. And this is the final format that we want the model to generate the queries for us. So this is just for this project, but as you can imagine, if you need different types of queries for your project, and if you need to perform searches on different angles than what we have here, you can easily modify the system prompt. Answer generation prompt, it is for our final model, and it is a very simple prompt that tells the model, this is the context, this is the question, and just give us the answer. Then we have generate subqueries. So we use that system prompt, we use our large language model for query generation, we create a chain, and we generate our different queries. And then we have retrieve for queries. So here we use each query and retrieve the documents. So for this project, I'm not going to perform search, for instance, on a SQL database, but we are going to utilize our vector databases. Then we have reciprocal rank fusion. So for ranking the documents, I'm using this technique here, right here. As I mentioned earlier, there are so many different techniques that you can use. I'm not going to go into the details of how we are ranking the documents. You can easily search for that. It is a simple formula. And again, this is one of the things that you have to fine tune in your project, and you have to make sure that the ranking strategy is aligned and it gives you the best performance for your project. And finally, we have generate final answer that integrates all the documents and passes them to our large language model, the answer generation model, and it gives us the final answer. And we wrap everything up inside process query. So now let's also see the performance of this method in action. So if I go into Fusion RAG, and if I ask my first question, how do containerization technologies work with orchestration platforms in modern development, and ask for the response. Before we get the response, I just wanted to clarify that in the project that I developed at the moment, we are not going to search different databases at the same time, but we are going to search our single database from different angles at the same time. So we perform multiple search queries on the same database at the same time. So this is the answer that it generated for us. Let's go through the logs and you will understand how it works right now. So Fusion RAG generated 4 different search approaches. Search approach number 1, how do containerization technologies work with orchestration platforms in modern development? This was our original query. Search approach 2, what are the containerization technologies and orchestration platforms, and how do they function in software development? Approach number 3, how do containerization technologies compare to traditional virtualization methods in terms of deployment and resource management? And approach number 4, what are some real-world examples of container orchestration in action, and what best practices can developers follow when implementing these technologies? So we get our 4 different queries. We fetch the information for each one of them. As you can see, we fetch 5 different information, 5 different documents for each one of those queries. We combine them, ranking them all, and we also perform the duplication. So we found 16 unique documents across all searches. So in total, we got 20, but 16 of them were unique. Top ranked documents based on consistency across search approaches. Rank number 1, this was the score that we got based on the ranking strategy that we implemented here. And this is the piece of document that we retrieved. This is the second piece, third piece, etc. So these are our rankings. And then we combine all the information, or we integrate everything into the same prompt for our final large language model to generate the final response for us. So this is what I'm doing right now with this project. For each database, we perform multiple queries and multiple searches at the same time, and we generate the final answer. And this is the answer that our system gave us for this question. Let's go through the second question. Let's change the database. What is the complete process for handling a damaged international shipment? Perfect. So we got the response. To handle damaged international shipment, follow these steps, and these are the steps from our document. And this is, again, what happened. 4 separate search strategies. Approach number 1, 2, 3, and 4. We fetched 20 different documents. Again, 16 of them were unique. And these are the ranks and the scores for each individual document. And we got the final response from our system. Let's ask the last question from our news articles. How are recent AI developments changing both healthcare and business operations? We got the response. We went through the same process. We fetched 20 documents. This time, 14 of them were unique. We ranked them again, and we passed all the information to our final large language model for processing and for generating the final response. So as you can imagine, Fusion RAG has a lot of potential, especially if you want to interact with different databases and you want to fetch different information. You want to perform, for instance, web search, interact with SQL databases, and or interact with any type of database that is relevant to your project. This is a very powerful strategy, but this strategy can easily turn into a multi-agent strategy, which then gives you a much more superior performance. Okay, so now let's go through our next strategy, which is called a speculative RAG. This is a very special method. It has very unique use cases, which you will see in a moment. And if you want to implement this method successfully, you have to take into account so many different factors. So let me go through the description first, then you will understand why this is a very special technique among all the techniques that we have covered so far. So a speculative RAG is an advanced framework designed to speed up and improve the QA process by using two AI models in a producer and checker setup. The idea originates from a speculative decoding used to accelerate text generation and applies it to retrieval augmented pipelines. In this architecture, a smaller or drafter model quickly generates several possible answers in parallel, and a larger or verifier model then evaluates, scores, and selects the best response. Think of it like having multiple junior analysts write reports and then a senior expert reviewing and approving the best one. This approach delivers the best of both worlds. It is faster, and in certain scenarios, it can also achieve a higher quality because we have a final verification that is performed by a larger model, which is more capable and more powerful. So from a high level, we get the query, we perform our retrievals, we then go through parallel draft generation step using different smaller models. Then we have draft evaluation using our larger model, and we have final selection or merge before we show the response to our user. So let's go through some of the use cases together. The first use case is customer support and high traffic chatbots. For systems handling thousands of queries per second, using large language models for every request is slow and costly. A speculative RAG lets the small models handle most of the load, while the larger verifier checks and approves only the top drafts. The next use case is interactive voice assistance. Users expect real-time responses. This technique provides instant answers without sacrificing correctness. The verifier ensures factual reliability before output. The third use case is cost-sensitive deployments. When large model API calls are expensive, this technique reduces cost by calling the large model only for validation, not full generation. And finally, expert or ensemble QA systems like legal, medical, or financial systems. Even outside of latency concerns, generating multiple candidate answers and selecting or blending the most accurate one improves factual precision and reliability. Example scenario. Let's imagine that our user asks, what is the capital of Brazil? Document retrieval, as usual, the system retrieves documents about Brazil. Some mention Brasilia, which is the correct answer, and other mentions Rio, which is a historical capital. Parallel draft generation. The small model or drafter spins up multiple instances in parallel. Draft A, the capital of Brazil is Brasilia. And draft B, the capital of Brazil is Rio. So the first one is based on the retrieved document stating Brasilia is the capital. And in the second one, the answer is a little bit ambiguous and the model gives us the wrong answer. These drafts are produced very quickly due to the drafter's small size. Then we go into the verification step. The verifier model checks each drafter's factual alignment against the received context. Draft A matches the evidence, and draft B contradicts with the context and with the retrieved text. The verifier assigns high confidence to draft A and low confidence to draft B. Then we have the selection or the fusion step. The system selects draft A as the final answer, or in complex cases could fuse elements of multiple drafts if they complement each other. Final response, it gives us the correct answer. So what are the challenges here? Coordination complexity. It requires careful orchestration between drafter and verifier, plus parallel job management, because if we have multiple models running at the same time, if we want to reduce latency, we need to implement a solution for that, a strategy for that, and parallelization is one of them. Verifier overhead. Too many drafts can cancel out speed gains. Balance quantity versus verification time. Cost management. Multiple model calls per query. You must optimize draft count and verifier usage. Next, evaluation reliability. The verifier's scoring logic must be well-tuned to avoid over-trusting weak drafts. And finally, context consistency. All drafts must reference the same retrieved context for fair comparison and validity. So at this point, you have probably noticed that this RAG technique is a very good candidate for when your system is going through a high traffic, or if you are working with open source models, and specifically if you want to work with edge devices. So similar strategies are being tested in Anthropic and also in OpenAI's speculative parallelism for faster GPT inference. These are some of the sources that you can go and check. And for practical setup, I mentioned that small drafter model can run locally or, for instance, on edge devices. Large verifier model is hosted in a cloud for final validation. And this is ideal for hybrid setups, for instance, mobile plus server to minimize latency and cost. The next node that I want to talk about is context consistency. Here I mentioned that this is a good practice to use the same retrieved context for all the smaller models for fair comparison. But that is just one way to do it. Let me give you another example. Let's say that you want to combine this strategy with Fusion RAG. You want to fetch information from multiple databases, you want to use open source models, and you have to process a lot of information. So one way to do it is to add a small large language model in front of each one of those individual resources. With that strategy, you can process each chunk of information separately, get the response from each one of those small models, and then pass all of them to a large language model for verification and for preparing the final answer. So what I explained here is just one way of doing it. But at the end, you can combine these techniques together. You can even change any of these nodes that I mentioned here to come up with the best performance for your own project. And for our project today, since I didn't want to use open source models, I decided to just simulate the engine for speculative RAG. And this is how I implemented our project. So we are going to get a query. For that query, we are going to perform document retrieval, just like what we did for standard RAG. Then we will pass that to multi-perspective document sampling. So in this step, we want to break down those retrieved documents into separate groups. Then I pass each separate group to a separate large language model. Since I'm using GPT model at this phase, I will pass each one of them to a GPT model. That model is going to come up with a possible response. This is draft response 1, 2, and 3. Then we perform quality verification and scoring a score from 1 to 10 because we want to select the best response for our final language model. Then we combine all the responses, all the selected responses, and then we pass them to our final large language model to generate the response for us. Again, I'm going to use GPT model for all the large language models in this system, but I hope you understood that what are the best cases for this strategy and when you can use this strategy to get the most benefit out of it. So let's go through the code and let's see how this one works. And also keep that in mind that this is just a simulation of how a speculative RAG would work. But as I will go through the code, and especially if you read the code by yourself and when you understand everything in detail, you will understand that there are so many different parts of this pipeline that can be optimized and that can be adjusted based on your needs. So from the top, we have a drafter large language model and a verifier large language model. Let me show you the config for this. So I'm using GPT-4o Mini for both. For one, the temperature is 0.7, and for the other one, the temperature is 0. And we are retrieving 6 documents in this pipeline when we perform the vector search on our database. Then we have setup generators method. Here we prepare the system prompts. So the first prompt is for our drafter, which is based on the provided evidence, answer the question comprehensively. And then we have our second system prompt for the verification or for our verifier. You are a strict verification agent with a specific focus area. We provide the focus instruction. Evidence available, this is the evidence, question, and the proposed answer. Then we also explain a scoring system. So we want this model to give us a score for each individual draft. So score 1 to 2, as you can see, this is very poor, and score 9 and 10, it's exceptional, and it's a perfect response. Then again, we emphasize that this is your focus, and just also keep that in mind that I fine-tuned this prompt for GPT-4o Mini, and that is why we have 2 focus instructions here. This is how eventually I saw some good responses from the model, but this is, as you can imagine, is not the most optimized system prompt for our model right now, or for the model that you want to use. Check for these specific issues. Then the model learns how to reduce a score if it sees a problem in one of those drafts. We go through our multi-perspective sampling. So here, when I retrieve 6 documents, I just divide them into 3 groups, and each group contains 2 different documents. But if we have less documents, this is going to also divide them into separate groups. In one of them, it's going to create an overlap. And as you can see, right now I'm using very simple techniques to create our groups. So these groups, in the example that I mentioned earlier for combining a speculative RAG with fusion RAG, can be the output of different searches from different resources. Or you can implement a more sophisticated strategy and make it more meaningful for your project. Then we have our generate draft response. So we create our chain and we generate the draft. And also we have verifier response. We create the chain and we generate the verification for each individual draft. So let's go through each one of the focuses. We have 3 focus areas. We have factual, completeness, and clarity. So just to give you an example, we have 6 documents. We will divide those 6 documents into 3 different groups, and we will create, or we will generate, a response and a draft for each individual group. Then we will run 3 different verifiers, one for each individual draft. That verifiers, the first one, would check the first group and will evaluate it based on factuality. Then our second verifier checks the second draft and evaluates it based on completeness. And the final verifier that checks our final draft evaluates that draft based on clarity. So as you can imagine, there is another issue here. So I have 6 documents that are coming from the same vector database in this pipeline. Then we divide it into 3 separate groups. Each group contains 2 unique documents. And we evaluate each group based on a different criteria here. So this is not perfect. As I mentioned, this is just for simulation. But when you want to implement this method in a real project, you have to also optimize this step. So there are different things that can happen. For instance, you can evaluate all those individual drafts based on its factuality, completeness, and clarity at the same time. Or you can evaluate the resources that are coming from different databases or different search strategies with a different criteria that is not defined here. So my point is, if you want to implement this strategy correctly, there are so many different steps that you have to adjust and optimize. So we pass the focus instruction to our verifier, we run the verifier on our drafts, we get the score, and we select the best score, and we provide it to the user as the best response. So let's go through our code and let's see how this strategy works. And for this method, I'll just pass one example to show you what happens in our pipeline currently. So how do containerization, orchestration, and cloud computing work together in modern software development? Okay, we got the response. This is the response from our system. And now let's go through the logs and let's see what happened. So we retrieved the documents from our knowledge base. Number of retrieved documents were 6. We are creating 3 different document perspectives from 6 total documents. So these are our 3 different groups. And as you can see, each group contains 2 unique documents. Then we generate multiple draft responses in parallel. So draft number 1, generate response using 2 documents. This is the number of characters in our response. For draft number 2, we generated another response with this number of characters, and this is for draft number 3. Then we pass each individual draft to our verification model. So critically, evaluating quality of each draft response. Draft number 1, focus, is on factual accuracy and evidence. The score was 9, but I also add a variation to each score that comes out from our verifier. Whenever the model comes up with a score, especially after I started to test the performance, I noticed that GPT-4 Mini tends to come up with very similar values for different documents, especially the documents that we have in our vector database currently. So I started to add or remove 0.3 from our score randomly. So that's just a random variation to break ties in case it happens. So this is the variation here. And as you can see, so this is a number between 0 to 0.3 that we are reducing. And here it's reduced 0.2 from our 9, which was at the original score. So strict quality score is 8.8 out of 10. This is, by the way, another aspect that you have to adjust based on your documents. So this is what I saw based on the documents that I have at the vector database. And as you know, these documents are just simulated quickly to create a vector database so we can work with this chatbot. But when you start interacting with real-world documents and with your project docs, you have to find a way to break ties and take into account other edge cases that might happen with this pipeline. For draft number 2, the focus is on completeness. The score was 9. With variation, we gave it an 8.9. And for draft number 3, the focus is on clarity. The score was 6, and with variation, we gave it a 5.8. Then we chose draft number 2 because it had the highest score, and we showed the result to our user. So this is the result, and this is coming from draft number 2. So this is how this pipeline works. Now let's go through our next method, which is Agentic RAG. So this is my favorite RAG among everything that we have discussed so far, because this strategy has no boundaries. Agentic RAG builds on the standard retrieve and generate pipeline by adding a layer of intelligent decision making. Instead of following a fixed process for every query, the system acts like a team of specialized agents, each responsible for a different part of the reasoning and retrieval process. So before I go through the agents that I have for my project, I just want to explain that the project that I have right now is coming from a tutorial from LangChain, and these are the agents that are implemented in that project. But when we talk about Agentic RAG, you can think of it as a customized RAG pipeline that can do anything that your project needs. So as an example, when I talked about Fusion RAG, I pointed out that if you want to properly interact with a SQL database, you need a SQL agent. And if you want to have a RAG pipeline and a SQL agent next to each other, you are talking about an Agentic RAG strategy. So here we have a planning agent in our project that analyzes the user's question and decides what workflow to use. Just retrieve, or query multiple sources, or search the web. Then we have a research agent. This agent executes that plan, retrieves information from the most relevant sources and possibly external tools. Then we have synthesis agent. This step merges all gathered insights into one coherent and well-structured response. Then we also have a tool agent that, again, as I mentioned, can be anything. It can be invoked for external actions such as web search, running calculations, or calling different APIs. Think of it as a coordinated team of experts, planners, researchers, and writers, for instance, who collaborate dynamically based on what the question demands. So from a high level, we have the query, we have our planning agent that comes up with a strategy, then we have our research agent that executes that strategy, then we have the synthesis agent that generates the answer, and you can also add additional tools to your system, and you can customize the system to do whatever you want. Key traits. Adaptive workflows. Each query triggers a tailored sequence of steps. Multi-source orchestration. Agents can query local, enterprise, or external sources dynamically. Reasoning over retrieval. Agents can include verification, comparison, or even reflection stages as part of their plan. So everything that we discussed so far can be integrated into this system. How Agentic RAG makes decisions? The planning agent first classifies our query based on several characteristics. So imagine that we have a query that contains words such as latest today or a specific year. So our agent decides that I need to include a web search. If we have a complex query, for instance, a query that asks for a comparison or for an analysis over a specific topic, the agent might decide that I need a multi-source retrieval. And finally, cross-domain. For instance, if the query references multiple knowledge areas, for instance, legal plus tech, our agent might decide that I need to pull information from multiple knowledge bases. So based on this, it chooses a plan type, such as a simple strategy that just retrieves information and passes it to our large language model to generate the response. Or it can decide that I need a complex strategy that contains local plus supplementary retrieval, or a temporal strategy that contains local retrieval plus web search, cross-domain strategy that contains multi-source retrieval, and finally a comprehensive strategy that contains multi-source retrieval plus web search or plus any other tools that you want to execute in that workflow, and then we will pass the information to our large language model for the final response generation. Then the research agent gathers all required information following that plan, and the synthesis agent integrates everything into a structured final answer. So what are the use cases? Enterprise Knowledge Assistant, in which the company data is spread across HR, product, tech, newsfeeds. So simple queries hit one data source, complex strategy queries pulled from multiple departments, plus web updates. The next scenario is legal plus technical compliance assistant. So imagine that we have a query like, how do new EU AI regulations affect our data pipelines? The system retrieves internal compliance docs, plus engineering runbooks, plus EU sites updates. Then it produces a comprehensive cross-domain answer. The next scenario is market intelligence analyst bot. The query can be compare our current battery supply chain to the latest solid-state battery developments. Then our system pulls from logistic data, R&D reports, and web news, and then it produces a synthesized competitive analysis. And finally, smart customer support agents that can detect words like new or updated, that triggers a web search for the latest product release, in addition to support FAQs and docs. So keep that in mind that our current system for this project cannot do these tasks, but these are all examples of workflows that you can achieve with an agentic RAG. Let's go through an example scenario. How does our current pricing model compare to the latest pricing strategies used by competitors in 2025? Planning agent detects compare, which makes it a complex question, detects latest / 2025, then realizes that our query has temporal characteristics, and also detects our model versus competitors, and then the agent would decide that we also need cross-domain knowledge. So it chooses the comprehensive plan. That includes local plus competitor plus web search plus synthesis. So local, I mean local vector search or fetching data locally. Then we have our research agent. It first retrieves internal pricing docs for financial database. It retrieves past competitor analysis, for instance, a strategy knowledge base, and it also searches the web for 2025 competitor pricing updates. Then it passes all the information to our synthesis agent. This agent compares historical versus current pricing. It highlights trends and discrepancies, and it produces a structured evidence-backed report. So this is a workflow or a sample workflow of an agentic RAG system. Let's go through some of the challenges. Complex coordination. Multi-agent reasoning needs task scheduling and shared context management. Error propagation. A bad plan leads to wasted retrieval and irrelevant synthesis. Compute overhead. Each agent adds API or model calls. Orchestration cost must be optimized. Transparency. Harder to trace reasoning chains requires good logging and explainability tools. And finally, security and control. External acting agents such as API calls or searchers need a strict governance and guardrails. And these are just some of the challenges that a multi-agent system would face. I have another video in my channel called Hidden Technical Debt Behind AI Agents, and in that video, I cover all the challenges that a multi-agent system would face in a real-world scenario. Now let's go through the schema of our project for this video. So this is the agentic RAG pipeline that I prepared for you. We have our query input As I mentioned, we pass it to our planning agent, and it makes a decision on the strategy that we want to utilize to answer that query. It can be simple, local search only. It can be multi-source, cross-domain search, or it can be comprehensive, all sources plus web search. Then it passes the result to our research agent. That agent executes the plan. So this system can perform a primary search, which is a target dataset search. It can also perform cross-domain search, which is a related topic search. It can also use supplementary info, for instance, background context. This agent also has access to a web search tool. So it can also search the web when latest information is needed. Then we combine all this information and we pass it to our final agent. Our final agent gets all the information and it processes the response. It generates a comprehensive answer, and finally we analyze the information quality and provide transparency. So this is our Agentic RAG, and now let's go through our code and let's see how this RAG is implemented. All right, so the changes in this module starts with setup agents method right here. Here we initialize a large language model for each one of our agents. And if I show you the config, you can see that we have GPT-4o-mini for all our agents. We use temperature equal to 0, top k is equal to 3, and other retrieval top k is equal to 2. The reason behind this value is that this specific RAG strategy does not really care about which database we choose on our chatbot, because if it needs to perform a vector search on any of the available vector databases, it can do that for us, and this is the number of documents that it can retrieve from each one of those databases. The next new method is detect query characteristics. So this method classifies the query based on the information that it contains. So if it contains these words, it would say that it has temporal characteristics. Same for complexity words, domain keywords, etc. So it gives us the class and it tells us the characteristics of our query. We pass the result of this function to our planning agent. Based on the characteristics of our query, planning agent comes up with a plan. So for instance, it can say that we need a local search, we need cross dataset search, we need a web search, and finally we need to pass all the information to our synthesis agent. And then it gives us the plan. We pass the plan to our research agent. Research agent is responsible to execute the plan for us. So based on what was listed in the output of our previous agent, the planning agent, it starts to execute those steps one by one. It performs a local search for us, it can perform a cross-dataset search for us, and it can even perform a web search if it needs to. To perform the web search, it calls our tool agent method. So our tool agent method executes the web search and returns the result for us. For simplicity, I limited the content size that we received from our web search because I just wanted to make sure that GPT-4o-mini can process all those information. And we also have our synthesis agent that receives all the information combined together, process that, and gives us the final response. Now let's go to our chatbot and let's test our agent. For the first question, I want to ask, how do modern DevOps practices affect customer support and business operations? Okay, we got the response. This is a comprehensive answer. Let's go through the logs. So in the first step, we classified our query. And the planning agent decided that multi-source search is needed and also cross-domain query search is needed. So we pass it to our research agent and it started to execute the strategies. The first step was to execute a vector search on the main database that I chose here. From that, it found 3 primary documents. So this is the tech docs that we chose here. But then in the next step, it also performed a vector search on our FAQ data, and it found 2 relevant documents. And it also performed another vector search on our third database, which was news article. Again, it found 2 other documents. So together, it found 7 relevant documents. Then we processed those documents. Technically, we combined those documents in this step, and we passed them to our final agent for providing the final response to us. So this is the workflow in the backend. Let's ask another question, though. Here, this word right here, recent, should trigger the pipeline to use also the web search capability. Perfect. So we got the response, and let's see what happened. So we classified our query. Then the planning agent, based on the classification result, decided that we need a comprehensive research. It also has temporal characteristics, and we need cross-domain query. So the research agent started to execute our plan one by one. First, it found primary information from our local database. It found 3 primary documents from TechDocs. It also found 2 extra documents from FAQ data, and also found 2 extra documents from news article. Current information is needed as well, so it requested a web search. It called tool agent. Tool agent performed the web search for us, and it returned 353 characters from web search. The reason that I'm writing the number of characters here is because when I was adjusting the model's performance, I just wanted to see the range of the characters that our large language model GPT-4o Mini can handle at the moment. Then we combine and we pass all those information to our final agent, which is the synthesis agent, and it gives us the final response. So what were the sources? News articles database, TechDocs database, FAQ database, but we also performed a web search here, and we went through one website to get the response for us. So this is how an agentic RAG workflow can work, but as you understood, there is no limit to this strategy, and you can implement and add any tool that you want, and you can customize this method for your own use case. And our final RAG strategy is hypothetical document embeddings, or in short, I'm going to call it HyDE. I'm not sure exactly how, what is the proper way to pronounce this. So I'm just going to call this HyDE for convenience, and hopefully I'm not wrong about that. So HyDE, short for hypothetical document embedding, is a retrieval technique that reimagines how queries are handled. Instead of directly embedding the user's question for retrieval, HyDE first has the language model generate a short hypothetical answer, a fake but plausible document that might answer the question. That text is then embedded and used to search for real documents similar to it. In essence, the AI asks itself, if I were to write about this topic, what would I say? And then uses that imagined text to find real information. And with this strategy, we can get very interesting results. Because the hypothetical document often includes key phrases and richer context, it can surface more relevant or hidden matches in the knowledge base, even when the original question is oddly phrased. So from a high-level perspective, we get the user query, we generate a hypothetical answer to that query, and we embed that hypothetical text. Then we perform a vector search using this embedding that is coming out of our hypothetical answer to get the final answer generation. So what are the use cases? Domain-specific or unfamiliar queries. When the retriever doesn't recognize the user's phrasing, example, in medical, legal, or scientific queries. The LLM-generated hypothetical answer rephrase or expands the question with domain-appropriate terms, improving retrieval accuracy in zero-shot settings. Long or complex questions. Verbose or convoluted queries often embed poorly. HyDE first distills the essence of the question into a short mock answer, which captures the right semantic for retrieval. Example, in The Lord of the Rings, what Elvish word does Gandalf use for friend at the Mines of Moria? Hypothetical answer. Gandalf says, melon, which means friend in Elvish. Embedding this hypothetical answer is going to hit directly to the correct passage. Improving recall in sparse datasets. When a standard retrieval misses results, for instance, it gets low recall, HyDE can boost coverage without retraining. It acts as automatic query expansion. The hypothetical answer introduces related terms that help the retrieval find more matches. Tools like Haystack, LangChain, and LawIndex now support HyDE for this reason. And finally, cross-language or user-speak queries. If users write informally or in mixed languages, HyDE can translate them into formal, knowledge-based language. For example, how can I get a refund because my gadget was DOA? Hypothetical answer. You can request a refund for a dead-on-arrival, in parentheses DOA, device by contacting support within 30 days. Matches knowledge-based article return, and refund policy for defective products. So this is a very interesting example. Let's go through an example scenario. What mythical creature is half eagle and half lion, often seen in medieval heraldry? Hypothetical document generation. The creature you are referring to is the griffin, a mythological being with the head and wings of an eagle and the body of a lion, often featured in medieval heraldry. This hypothetical text wasn't retrieved, it is imagined, but crucially includes the keywords griffin. So imagine that you want to perform a vector search on the original question versus what the large language model generated as a hypothetical response. So the system embeds this text, converting it into a semantic vector representing its meaning. Then we perform a vector search using this new embedding that we just received from our large language model. And finally, we pass the documents to our final large language model to generate the response for us. So what are the challenges here? Inference costs, because we are adding a generation step before performing a vector search. Hallucination risk, if the hypothetical text includes false details, we may retrieve wrong documents. Evaluation difficulty, hard to measure when generated hypothesis helps versus when it hurts. Control needs that would require guardrails such as truncation or term preservation to keep hypothetical documents focused and relevant. So there are some notes here also for you to understand how well established this strategy is. As you can see, Haystack, LangChain, Llama Index, as I mentioned before, are already utilizing this method. And this is the project that I've prepared for this strategy. So we get the query input, we pass it to a large language model to generate a hypothetical document for us. Then we vectorize that document, we perform the vector search, and we pass the retrieved documents to the final large language model to generate the response for us. So let's go through the code and let's see the changes in this one. So let's directly jump to our new method here, setup HyDE generator. So we have a system prompt, and this system prompt contains 3 different prompts in it, because depending on what database our user is interacting with, HyDE is going to come up with a relevant document to that specific vector database. So for instance, if we are interacting with tech docs, we tell our large language model that you are a technical documentation expert, write a comprehensive explanation that would appear in technical documentations about, then we insert the query, generate a response that is less than 500 words long. We also want to make sure that it is short because we are going to vectorize this information, and if it is very long, then it's going to hurt the accuracy of our vector search. And your response should be detailed, technical, and include these criteria, right, as if this is from an authoritative technical source. So this is an example system prompt that we want to pass to our large language model. So as you can imagine, we also have a generate hypothetical document. So we prepare our large language model, we prepare the chain, we pass the query to it, generate the document, then we convert the output and create an embedding, and then we perform the vector search using the new embedding that we just received from our large language model. And finally, we pass all those information to another large language model to prepare the response for us. And this is the system prompt for that last large language model. Okay, so this one is pretty straightforward. Let's jump to our chatbot and let's test this final strategy. So let's choose it and let's ask our first question. So for the first question, I want to ask, what are the security considerations for cloud computing? All right, so we got the response, but let's go through the logs and let's see what happened. So we are creating hypothetical document for improved retrieval. Generated HyDE document. Security considerations for cloud computing. Key concepts and definitions. Cloud computing refers to a delivery of computing services, etc. So the model came up with a comprehensive answer that would resemble an accurate answer from a database. Then we vectorized this output, we performed the vector search, and we found 3 documents. We passed those documents to our final large language model, and it gave us the final response. So let me also ask one last question for our news articles. How is technology changing healthcare? Okay, so this is the answer, and now let's see what happened here. How technology is transforming healthcare, a new era of innovation. In recent years, technology has emerged as a pivotal force in rephrasing the healthcare landscape, driving improvements in patient care, operational efficiency, and data management, from telemedicine to artificial intelligence. So, as you can see right here, I didn't mention anything about any of these technologies, but the fact that the model included all these technologies in its hypothetical document would allow us to perform a much more accurate vector search on our database. Then we used it, we performed the vector search, and we passed the result to our final large language model to generate this response for us. So that was the last technique that I wanted to cover in this video, and together we went through 8 different RAG techniques that are being used heavily in industry. This is also a summary table that I prepared for you, which shows all the techniques that we covered, when to use them, and their key strengths. So with that, I'd like to thank you very much for watching the video, and I hope to see you in the next one.